So we want to look at bivariate analytics, bivariate linear equations. It's very, very simple, very precise, very concise. So let's suppose that we want to explain the consumption pattern of household. Consumption here is not just consuming food, but it's also about consuming anything. It can be houses, it can be consuming the shed, transportation, anything that you use. Now you have the consumption represented by C here. And then there's an economic theory that says that consumption is influenced by income. Now, that is assuming that the good is what type of good?
Normal good.
Good. Now, if it is an inferior good, it means that there is one relationship between consumption and income.
Invest.
Invest, very good. Okay. Now, the relationship is not exact. It's not deterministic. It's not deterministic, meaning that there's a stochastic version of the relationship, because there are other independent variables that can also influence, in addition to the error term, other than the income. You can have the size of the family can affect your consumption. Okay, if your family size is big, you are very careful. Taste and preferences, and of course, the stochastic noise. So this is a simple regression that we can have, where the alpha is a constant term. It has no economic meaning. Okay? It is only there for aesthetic purposes. The error is an unexplained factor, assuming that time is irrelevant here. Now, we call this the population relationship, okay? And it's assumed to hold for all the households in that particular sample. Okay. Now, what we want to do is that we want to know the extent to which the income affects the consumption. And that is determined by the beta parameter. Both alpha and beta have to be estimated because the existence of the error term means that they cannot be calculated exactly, because the error term will distort. And so the essence is to go to that error term and handle that error term, minimize that error so that the clear relationship between the alpha and the beta are manifest. Now, the estimator that is used to do that is known as ordinary least squares. So ordinary least squares is an estimator. It's not an estimate, but the ordinary least squares is an estimator that can help you to generate or produce an estimate. Another thing apart from OLS is GLS, generalized least squares. We shall look at some of them. Okay, we have GMN. There are several, estimators that one can have. What it does is that it transforms the beta and alpha parameters into an estimate. And the estimate will tell you how well the model is doing. So we know this. These are just walking through things that we know. Now let's get a bit of details about how the whole thing is, the data generating process. So let's assume that we have a random sample from the population. A sample is consisting of pairs of consumption and income. So we have maybe 20 consumption patterns from 20 families. And each one, we also have their income patterns and income families. So each one is from 1 all the way to N. That is the I. The consumption will now start from C1 all the way to Cn, and the income will start from Y1 all the way to Yn. Now, the relationship between the two is specified basically like what we've done here. There are basic assumptions that make this real. One of them is that expected value of the error given the independent variable, Y, is 0. Now, this one is a common knowledge, okay, for regression. We call it the normality assumption. But note that this is for every household. It's not for one. So every household, every subject, every observation will have an error, because you must know the difference between the predicted income, the predicted consumption, which is the estimated value, and that of the actual consumption. Now the gap between that is defined by the error. So that means that given the fact that there are other factors that can influence consumption, it means that the error will be big if the relationship is just bivariate like this. So you will notice that in a bivariate relationship, the coefficient, the beta parameter here is smaller. Okay, and the p-value is bigger than it would have normally been had other factors been added. So when other factors come, your real relationship is even evident, okay, than it is. If you consider the error term to be 0, then it means that the expected value of the error given that is left with only this, the alpha plus the beta. And that will tell you that there is a conditional expectation of consumption given income, assuming, of course, that the error term is 0. So this is an assumption that has to be there. It's an assumption of normality. The residual, or the error term, which is also called residual, is the one that is said to be normally distributed with a 0 mean, because you expect it to be that. But not only with a 0 mean, but it must also be homoscedastic, meaning that the variance of the error should be a constant. Now, remember that the variance of the error is also given as the error square. And so if you square the error, you dissipate the negatives, okay? You create an absolute value, and so you'll be able to find the actual constancy of the error. Opposite of homoscedasticity, which is a constant variance, is heteroscedasticity. You know this already. There is another error. Now, who can tell me the difference between the covariance of the error I and error J? What is it? Who can tell me this? What is the difference between the error I and error J? Because we are going to use this one going forward. What is the difference between the error I and error J? Francis?
I think we are looking at the individual error against the estimated error.
Not exactly. What is the difference between error I and error J? Ima?
No idea, sir.
Albert?
Look, they are independent.
No, really. No. What's the difference between error I and error J? Newman, are you there?
Yes, Doc. I'm thinking the error J would be the household error, and then the error I would be the individual within the household, if that's correct to put it.
Household error, and then the individual within the household. No. So each household is an individual. Take note. So you have how many households? 20, say.
20.
And then each household has a consumption value. Let's say 2,000 Ghana cedis every single year. And then the consumption value is dependent on the income. And you look at the income, okay, every year, whereas this one, every year the consumption is changing between 2,000, 3,000, 4,000, 5,000, or let's say even monthly. And then you have the income. The income is say 4,000, 5,000, and they are only consuming 2,000, 3,000, but the income is 4,000, 5,000, 6,000. Okay. Now, the gap between the consumption and the income is this error. But the error I is for one individual, whereas error J is for another individual. Take note. So the same way an individual in Latabi Okochi will have a different consumption from an individual in Sakumono. The same way the error for the individual in Latabi Okochi, which is error I, will be different from the that of the individual in Sakumono, which is the error J. So the error I and the error J are all errors, just that they are different. And to indicate that they are different, we call one I and we call the other J. Does it make sense?
It does.
If a household's consumption is greater than that of the income, there is no reason to expect the household's consumption to be high relative to that of the income, okay, or low. In other words, this situation says that there is no serial correlation. In other words, the errors are orthogonal, which means that they are not correlated. Okay, there is no correlation between the error. Now, why is that so? I'll give you an example. Let's say that an increase in the consumption of a person living in Sakumono is as a result of the increase in the income of that same person. Okay, so that person won a lottery, and then the person got an increase in income, and that led to an increase in that person's consumption. So he moved away from Sakumono and bought a posh multiple houses in East Legon. And then the person who is also in, what do you call it, in Latebi Okoshi, also moved to buy a house in East Legon. All of them increase their consumption, not knowing that the guy who is in Latebi Okoshi happens to be a brother of the one who was in Sakumono and moved to East Legon. So there is some correlation in these errors. So there's something affecting the behavior of these. You can't find it within the guy inside Latebi Okoshi directly, but we don't want that to happen. Oh, by the way, I hope you understand the analogy I gave. Albert, do you get it?
Yes, Doc.
So you see, it's errors, so you don't see it. Both of them have come to move there. You don't see it. That is why sometimes people get into politics. All of a sudden, then they start building some houses. Then people start beginning to question that. Then you tell you that, oh, it's because I have a business that is running. It's but you've had that business all these while. We never saw you. That's where we are. Where we are. Okay, because there is some correlation there. But we don't want any serial correlation. It is invisible and it's not clear because that of income becomes clear. The income is clear. We can track it, but it's invisible. It's an error. It's disturbance. It's behind the scene. It's stochastic. And therefore, we don't want that to happen. Now, how do you make that not happen? We'll see. There's a way to check that. So that is it. So you will notice that most of the errors, most of the assumptions of regression, the axiomatic properties of regression are all related to the errors. Okay. So finally, if all of these things are happening, if they are all met, then it means that we can say that the error is independently and identically distributed normally, with a zero mean and then a constant variance. It simply means that we want the errors to assume normality. There is another assumption, and that is independence between the error and then the dependent variable. Now, who can tell me, why do you think that there must be zero covariance between the error and that of the independent variable? Remember that Y is independent variable. I know that the ones you guys have been learning in the past, Y is normally the dependent and X is independent, isn't it? But here, I want you to look at Y as income, independent, and C as dependent, consumption. So this is a relationship between the explanatory variable, the regressor, the predictor variable, and that of the noise term. And they say that there must be no covariance, or better still, no correlation. There must be no dependency Why? There's a name for this. Who can remember? Neiman, do you know the name for this?
No, Doc.
You'll be asked to derive it, too. Apart from knowing the name, you got to derive it. God, do you remember the name for this? Between the independent variable and that of the error.
Not immediately, Doc.
You remember the issue about endogeneity?
Yes.
What comes into your mind when we talk about endogeneity?
So when it comes to homogeneity, we're just suggesting that there is some correlation between the independent variables and the error.
I remember. You are not there. Yeah. But that's it. It's a big issue. Okay. It's a big issue in our analysis of regression. And why do you think that this should not happen? Albert, why do you think this shouldn't happen?
Look, it shouldn't happen because you want to separate the noise from the predictor. If you don't do that, then your results will be wrong. Your interpretation of the results will not be accurate.
It's a big issue. It's a big issue that you have to solve. And there are several things you use to solve it. Okay, like instrumental variable regression, two-stage least squares, GMM, okay, and then Lubel approach and all of those things. If you are, let's take for example, you are a consumption, and then your consumption is affecting your income is affecting your consumption, just as we are seeing here. So your income is an independent variable, your consumption is the dependent variable. The moment your income goes up, your consumption increases. And then somebody comes to it. So people thought that is your income that is going up. But behind the scene, it wasn't your income that is actually going up. Your income, until I say, the politicians people become suspicious of them. Your income is not going up. All of a sudden, you enter into this arena. We know your income. And all of a sudden, your income goes up. Now, it could be that something is affecting your income, we don't know. So in this case, your consumption that is going up is not because of your income. When I say your income, it's not because of your salary or business income. No. Because there might be that there is cocaine behind the scenes that you are doing. There is some criminal activity that you are doing. But people would think that it is your consumption, your Y, that is affecting your C, which is unbeknown to others. So this is a hidden activity that has to be eliminated. And in the process of that activity is called endogeneity. Now, what is the opposite of endogeneity? It's EX. What is the opposite of endogeneity? Lawrence.
Doc, exogeneity.
What is exogeneity?
So then that would be, I'm just missing, maybe the relationship between the two.
What two?
The noise or the residual and then the independent variable.
Not exactly. But what is really exogeneity? And you have to say it from the understanding I just gave you. Is exogeneity good or bad?
It is also not good.
Hey, Papa, relax. Drink water. There's a friend I have, he's got drink water. Exogeneity is good. Anand, why do you think exogeneity? What is exogeneity? Let's get that first. Exogeneity means that particular independent variable, consumption in this case, it is influencing, the income in this case, is influencing the dependent variable consumption without the help of anybody. It's exogenous. It itself now is not being influenced by anybody. That is exogeneity. Now, watch this, watch this, watch this. If Y, which is consumption, which refers to, sorry, Y, which is income, which refers to your actual income from your salary or business. If that particular income is coming from, I want to just show you something. How do you screenwriting? Screen, how do you write? Okay, so let's say that you have Y, and this is from your salary or business, okay? And that Y is affecting the C, which is your dependent variable. That Y itself can be influenced by something, which is also another independent variable, okay? What other factor can affect consumption? We spoke about the size of the family, okay? So let's assume that family size, so let's just call it S. If family size is affecting income before income will affect consumption, this is called multicollinearity. Watch it. Because the two of them are all independent variables between this and that. That is called multico. Two independent variables coming together to affect a dependent variable. But not just that, they are highly correlated with each other. So you can't really tell who is affecting. For example, suppose they tell you in your company that once you get 5 years, you'll be told to go and have your PhD for free. So your experience is the 5 years. Your PhD is education. So your experience and your education. Once you finish your PhD and your salary goes up, what led to the increase in your salary? Have it.
Your PhD qualification.
That is education. But what actually made you get that scholarship to go and do your PhD?
Your years of experience.
So your years experience, okay, both of them has helped you, and now you've gotten a higher salary. What led to that higher salary now? Is it a years of experience or is it PhD education that you had? Both of them contributed. So you cannot really disentangle which one is actually leading to your higher salary. So in this case, your education as well as your experience are multicollinear. Because the relationship between them, the correlation between them is 0.9. Now that is not the same as endogeneity. Endogeneity is the same thing, but between your education and the error. I'm bringing something up. Your education and error. So watch it. Your experience here can be influenced by an error, making it endogenous. Okay, it's bringing about endogeneity problem. And that same experience may be highly correlated with education, bringing about multicollinearity. But if experience is not being influenced by any error and is not being influenced by any other independent variable, that makes experience what? Clarence. It makes experience what?
Endo. That would be endogenous.
Not endo.
Exogenous.
Exogenous. Guys, pay attention. That will be exogenous. So these three terms, you should know them carefully. Exogeneity, endogeneity, multicollinearity. Note them, I've told you. Understand them, okay? Because it's not just the mathematical modeling, but it's having an understanding of the mathematical modeling. That matters here. Exogeneity is when you are not being influenced by anybody before you influence the dependent variable. And for you to be exogenous, you must be an independent variable, guaranteed. But not all independent variables, not all exogenous variables are, not all independent variables are exogenous. But all exogenous variables are independent variables. Take note. All exo are independent, but not all independent are exogenous. Why? Because some of the independent variables are also endogenous because they are correlated with the errors. And some of the independent variables are multicollinear because they are correlated with other independent variables. So that is the essence of this. And in this assumption, you don't want any endogeneity. That is a zero covariance. That is the assumption of the zero covariance. How do you even clear this thing? Good. So you should be able to know and understand these things. We don't want any of these things to happen, but we want exogeneity to be there. As for exogeneity, we want it to be there. Next one. The next one is linearity. Linearity we know. We'll come and look at the linearity later times. How to handle linearity. Linearity is an OLS. OLS is linearity. Linearity. When the relationship between the dependent and independent variable are linear, meaning that if consumption rises, income will rise. It's consistent. If consumption falls, income will fall. Consistent. If consumption rises and income falls, that is also consistent. But we don't want a situation where consumption is rising and then income is falling. Then another time consumption rather falls and then income rises. No, no, no. We want that thing to that pattern to continue, and that is linear pattern. The other one is that Y must be deterministic. We know that already. So I've spoken about multicollinearity. Okay? We don't want that to be there. Well, you want a bit of multicollinearity to be there. Okay? You don't want perfect multicollinearity. Who can give me an example of a perfect multicollinearity? A perfect multicollinearity is a dummy. A dummy. Okay. The opposite of a male is probably 1 minus female. Okay. Opposite of a male is 1 minus. So if a male is there, 1 minus a female is the same male. If a male is 1 and a female is 0, okay, 1 minus a female is a male. So dummies are, perfect. So you don't want a situation where you bring 2 factors. That's why we normally take 1 and create a dummy. You can't bring male and then you bring female. Because you are going to experience that whole perfect multicollinearity. All right. And then no specification bias. You see that sometimes you specify the model and then you... Now, when assumption 1 to 4, when they all hold, the OLS is said to be best linear unbiased estimator. In other words, the Gauss-Markov theorem has been satisfied. You need to learn how to... Okay, so watch this, guys. Once you have been able to satisfy all the assumptions, 1 to 4, then we can say that the beta parameter, that is the marginal effect of the beta of the independent variable on the dependent variable, is exactly as it would have been had we even taken the population. So we call that unbiasedness. Unbiasedness is where the expected value of the beta cap equals to beta. What is beta? Beta is a population estimate, the population parameter. But you see, the population is big. You cannot mimic the population. The population is unknown. But then, so because the population is unknown, the classical, the theorem, the classical, what's the name of this theorem? The theorem that says that as you approach, as you increase to infinity, then you are now reaching the point of equality. As the sample size increases and increases and increases, okay, you are approximating the population. The sample mean becomes the population mean. Central limit theorem. No, is it? Yeah, central limit theorem. Okay, so that's what
Theorem of large numbers.
Okay, the law of
Central
large.
limit theorem.
So I want you to see the beta as the true value of the coefficient, whereas the beta cap is the estimate. Usually, the beta cap is not the same as that, but we expect that to happen. If that happens, then there is no biasness. Okay? And that is known as unbiasedness. You should be able to prove unbiasedness. Let's do that. You should be able to prove unbiasedness. Okay? So when assumption 1 to 4, the basic ones, okay, when they hold, the OLS estimator is thought to be blue. I think I've indicated that. When the conditions of the OLS don't hold, the other estimators may be required. And that is true because what you need is that OLS is not working. So you have to try another estimator, okay, which will make it work, like GMM, like GLS, like WLS. We shall look at some of them. So let's go back and try to understand this whole expected unbiasedness. Let's try to understand it. The error is the actual consumption minus the estimated consumption. Now watch that this actual consumption is the CI. The estimated consumption is this one in the bracket because by then the error is gone. And so the error is just the same as the CI minus the alpha cap plus the beta. Now, we need to do something to this to be able to make it work. We need to minimize this error. Why? Because you want to have a clear relationship between the dependent and independent. So you need to minimize the error. Now, this is a minimization problem. So it's like minimizing something subject to something. Okay. But before you can minimize the errors can be negative and positive. So you want to kill the negatives. How do you kill the negatives? Anand, how do you kill the negatives?
By squaring
Take the
everything.
square, you square it.
You square
Square
them.
the difference.
So you take the square of the negatives of all values, and then now you can sum them. This error sum of squares is what you can now minimize. You take the error, you substitute the error here, you square it, put all of these values in there, and then you can now minimize. Minimizing here means differentiating with respect to alpha. If you differentiate this with respect to alpha, you see that this value 2 will come in front. And remember, because alpha in the bracket here, alpha is negative, that is why you have the negative there. Okay? And you set it to 0. And then you expand with the summation symbol. Once you expand with the summation symbol, you will notice that all of this, remember, it's only alpha that we want. We can replace the whole of this with this error because that is the error because the first part is the actual consumption and these minuses are the estimated. You set this to 0, negative, divide both sides by negative, okay, and you can kill even the negative. You can kill the negatives, and then you will see that whatever you've done here, we'll come back to this. Whatever you've done here, you have this as the error, negative together with the error. You can substitute that and differentiate with respect to the beta parameter. When you do that, you rather get this. Again, I've substituted the error with that. We can start with the beta first. With this equation, first equation 3 and equation 1. For equation 3, the first one we did here. Okay, this equation 3 up here, we can now define that because when you sum each one, when you divide each one by the negative and you sum, you are going to have the summation sign being applied to all of them. Okay. It was like this, it's just that it didn't have the y there. So you're going to have summation C, okay, and then minus summation. Of course, this one is going to be negative. So it's going to be plus summation alpha. But that summation is actually indicative of 1 over n, is a sample size. And so you get n multiplying the alpha cap. And then you, for the B, you will have the summation also coming here, which is 1 over the n. So you will have minus beta here, multiplying y, but together with the summation from the previous one. And that gives you this value. At this stage, you can make alpha cap the subject by dividing all of them by n. And so you're going to have sigma ci divided by n, sigma beta cap y divided by n. And now your beta, your alpha is going to be left with this whole thing divided by n is the mean. And then this whole thing divided by n is also the mean. And so alpha cap will be C cap minus n. I will ask you a question on this in the assignment. Okay, so if you don't understand this, let me know. All right. What about for equation 4? Well, equation 4 is very simple. From here, once again, you can clear the negative 2 and then expand the first one. You see that sigma y will multiply C. Okay. Then that same sigma y will multiply that. That's what you have here. Then the final one, sigma y will multiply the beta yi. That is this one. But because the y is coming here, the y will be squared. That's what you have here. At this stage, you are looking for beta cap. You divide both sides by sigma y squared. So this one will have alpha cap, then sigma y squared. Okay. And this one will have sigma cy divided by sigma y squared. Now watch it. That's sigma cy. That's sigma cy. Come on. Okay. That sigma cy, we can represent it because they are all being divided by, yi cap. Okay. We can now divide them and just indicate. By the way, this one is going to cancel. Okay. This one, when you divide the sigma y square by this, you're going to have sigma y square, sigma y divided by sigma y square. Okay. They will cancel, and then the other y will have the, anyway, we don't want that. What we want is a beta cap. And so you can now see that the beta cap is going to be sigma cy all over sigma y squared. This is a simple way of deriving the values. Let's go back here. What is that small c that we have here? The small c is when you have ci minus the mean. Small y is when you have the yi minus the mean. And of course, I've explained this one. These ones are when we did this, the summations. Okay. So each one of these are what you can use to find the beta value. You should be able to use this to derive the beta cap. And of course, from here, you can also derive the variance of the beta cap. The variance is basically the sigma squared, which is the error, the sum of the error, okay, divided by n, which when you simplify, you can just have this one. Okay. So we can now say that this estimated regression equation is this. Now look at this very one here. There's a problem with this equation. Who can tell me the problem here? Who can tell me the problem in this very equation? And the sentence up there. What is the problem here?
It still has the error term.
Exactly. Okay. So the error term is not supposed to be there. Okay. And that is what you should note from here, because it has the error term. So based on this, you'll be able to notice that you can use this whole thing to be able to find exactly the coefficient. Now, that is a simple regression approach. What about in a multiple situation? Well, typically in real life, we don't deal with simple things. Real life things are complex. So metrics helps you to be able to apply this whole regression to metrics. That's why we looked at metrics in the first couple of weeks. So let's assume that there is no one single independent variable, but there are multiple explanatory variables. Another name for the independent variable are the explanatory variables. So you have these multiple explanatory variables. Y is dependent on several things. You have the constant beta one, and then you have the error term. Okay. In that case, then we can create a matrix for the Y. As it stands now, this Y is also a vector, even though it's a matrix, because it's a one-column matrix. And then, if you look at the independent variables, you can combine all of them and create one matrix for all of the independent variables. They cannot be vectors at all. From the vector of the observation on this, anyway, I've spoken about this. And then we can create for all the independent variables here. If you look at these independent variables, they add, you see, so you want to have it like, instead of having consumption dependent on Y, you have consumption dependent on the Y, dependent on size of the family, dependent on something else. Okay? That is what the consumption is dependent on. Maybe this, you have the size of the family, but you also have the size of the house or something else, or the school fees and things like that. So X here is a matrix formed by putting all the other columns together. And you can see that on the basis of this, we can say that this small y is equal to capital XB plus the error term, where each of these are the matrices of the independent variable. And then those on the left-hand side is a matrix or a vector of the dependent variable. We can create the beta parameters as one column matrix. And then the error term also as one, because they are all going to be 1, 1, 1. In this case, they are not multiples. So you can see that this is an n by 1 matrix, and then the rest will follow as a k by 1 by 1, and then n by 1 matrix for the error term. This matrix, so each time I talk about y, I'm talking about consumption. And each time I talk about x, I'm talking about multiple independent variables in that case. But that's what's going on behind the scenes of R and behind the scenes of Excel. Okay, so now if you have the beta cap, the predicted value, okay, or the explained values of y can now be given by this, because we can kill the error from here. Okay. And now we can say that the error here, now remember, I'm trying to derive how do we get a beta cap. The error is y minus the y cap, but in a matrix form. The estimated y, which is a y cap, being subtracted from the actual y. This is the same as that, because this y cap has been defined as x beta cap. The error, which is not in a matrix form, the error is yi minus all of these, all of them, which are being represented by the x in a matrix. And we can therefore say that the residual in a matrix form, remember in a matrix form, this would have been squared with a sum. In a residual fashion, it is just taking the prime, because when you take the prime of the error, okay, and multiply it by the error itself, you can now get back the square of the error in the non-matrix form. This is what is known as the residual sum of squares. Now watch this. This same error multiplying itself is basically what you might call the variance of the error, the variance of the beta cap. Okay, I'll come back to that. So watch this. If you can replace each error which has been primed and an error which has not been primed, you can replace each one of them by that and expand this. If you expand this, this y will multiply that, giving you y prime y. This y will multiply that, giving you minus y prime x beta. This x minus x beta prime will multiply this y. Okay? So you will have it this way. Each of them will be primed. And then the rest will follow just like that. If you multiply this one by that, you get the whole of this. Just watch the primes are double when they are and not when they are not. Now at this stage, you can more or less group like terms here. And so you can see that the middle one, you can create a group like term for this. And then you can have the second one there. Given the fact that this y prime x is the same as the one without a prime, we can choose any of them, and then we can therefore say that beta cap prime x prime is y. We can now differentiate the residual sum of squares, which is the error, with respect to this beta. So here, this whole thing, we can differentiate with respect to beta. And what do you get? Okay. We can differentiate our respect to beta, set it to 0, and then on the basis of that, we can manipulate this easily. You've done this thing in your masters. But if you have a question here, you can ask me. Manipulate it, because when you differentiate it with respect to 0, and you set it to 0, and then you're going to get these very one. Because remember, anywhere there is beta, you're going to address it. And there is beta here, in this middle one, and there is beta in the latter one here. There is no beta in the first part. That is why this part here are set to 0. Okay. We set them to 0, and then we can now group like, and we can move this one to the right-hand side, equate the two, and then we can divide both sides. Sometimes that's what you might say, divide both sides by this. And when you divide, it becomes the transpose, the inverse of that. When you divide both sides by x prime x, and you can now have the value of the beta cap in a matrix form to be beta cap x prime x minus 1 x prime y. Learn to derive this in a matrix form. This is not complex at all. This one that software is doing, but you got to know how to do this at the postgraduate level. Now, this inverse, which is the beta cap x prime x minus 1 x prime y, this big inverse here, it exists when the matrix x prime x is a full rank. If it is not a full rank, it's not going to happen. And we did full rank, when we're looking at matrices. So it will require that the columns of the x are linearly independent of each one of them. Okay. Now, if you take this thing, there's a software called paleontological something. We used to use it in the masters. That software will give you the result. And you do remember Anna? Okay.
No, Doc.
There is a software. We call it PAST.
We were more used to the R.
Yeah, don't worry. We'll use the R. We are going to use R throughout. Yeah. But there's a software called PAST, and it does these things easily. eViews will produce an error if you try to use eViews. Okay? It will tell you that the x prime x is not invertible, even though it is invertible. So sometimes you can just take the x prime x and then put it into the result, and you get all the beta parameters easily. Now, let's take an example. This is a little bit complex, but it's a very good example. Let's assume that the independent variables are 2. Okay? And you have x2 equal to the lambda x1. Okay? One variable is just going to be a multiple of the other. So x2 is just a multiple of x1. x1 being multiplied by something. That's what it means. So if I multiply x1 by a lambda, I will get x2. If that is the case, then we can say that the x prime x is just one variable multiplying the other. And on the basis of that, we can get these matrix coming out of this x prime x. If only you have these elements. So this is one way. If you know the numbers, you can easily create your x prime x in this context. And you can substitute this one now for that, for the lambda x1, and then you can now get back each one of them with a lambda. Because x2, wherever you see x2 here, that's what it means. You represent that x2 by the lambda x1. So here there is x2, that becomes lambda x1. And here there is x2, that becomes lambda x1. Wherever there is x2, you do lambda x1. And remember, the prime, okay, the prime, which is a transpose, is the same thing but inverted in that regard. It's the same thing but turned from column to row or from row to column. Now, the second column X prime X is a scalar multiple of that of the first. We just explained it already here. And so we can say that the determinant of this X prime S is just a matter of finding the determinant of this, okay, which you learned last week, how to find the determinant. It's just taking this element and finding the determinants of it. In other words, we can represent this X prime S by a number. If this one is 2, and this one is 4, and this one is 6, and this one is 10, we can easily find the determinant of that and set it to 10. Now, what is the intuition here? Well, it is impossible to separate the effect of two variables. That's intuition. And so you can separately estimate their effect on the Y, in this case, a dependent variable, because they always vary together over the I. And that is why we say that if you have that of a woman and a man, or if you have a male and a female, you now have a perfect collinearity between them, because one can be replaced by the other or the inverse of the other easily. In fact, that is also why a woman does not testify in a court for a man, because the two are perfectly multicollinear. Well, I'm saying a woman when the love is strong, but the ones when the love is not stronger, that one you need. Because the one where the love is not strong, it can kill him. Imagine they say that your husband has stolen some money, and you know that, oh, as for us, your husband and wife. And not knowing that the wife wants to disintegrate your life. She will just come and say that she doesn't even know you. You paid her to come and do that. In that case, perfect collinearity doesn't exist. But collinearity on its own is a matter of degree. It's not a kind, it's of degree. So it is either you have more of it or less of it. The more closely a group of variables move together, then they are more likely they are going to be linearly dependent on each other. The less, that is also the case. And this can show up, when two variables are multicollinear, the variances can be very large. So you can have large variance metrics of the estimated parameter errors. Watch this, watch this. The estimate divided by the standard error, okay, will always give you the t-statistic. And it is when the t-statistic is estimated that you get the p-value. Now, the standard error, okay, is from that you get the variance, okay, or the square root of the variance gives you more or less the standard error. So that is what we mean by you normally want a very large t-statistic, okay, but that will require that the standard error is smaller for you to have large, because it's the estimate must be bigger. The standard error must be smaller for the t-statistics to be bigger, for the p-value to be smaller. Keep that in mind. Estimate must be bigger. Standard error must be smaller. T-test or t-value must be bigger, and the p-value must be smaller. That's how it goes. From top down again. In the regression result. So that is exactly the point being said here. Now let's prove unbiasedness, and let's prove the variance of the beta cap. You know this already. I won't spend too much time here. Unbiasedness, okay, meaning that the beta cap must be equal to the expected value. The expected value of beta cap is beta. That is unbiasedness. Like the mean of the beta cap is the true mean. That's basically what it means. How true is that? Well, in the simple case, the beta cap is this. In the simple case, this is the beta cap. Now you can see that at this stage, I've stopped using C and I'm using Y here, okay, for the dependent variable. And I'm using X for the independent variable. We can substitute the Y, which is the beta cap Xi plus the error, okay? That is it. Remember, I've included the error. I just substituted it into this. And on the basis of that, we can now split it. We can expand the top part. And when you expand the top part, you get this. Okay. The top part is split into two. The down part is the same. And so the down part is shared equally between them at the bottom, the denominator. Now, this left part will cancel. You are left with beta. What about this part? Remember, this part has an error. And because it has an error, if we take the expected value of all these, watch this. Okay. If I take the expected value of all these, the expected value of this one is this, is beta cap. The expected value of beta cap is beta, but the expected value of the error is 0. And so because the expected value of this error is 0, it means that the expected value of the beta cap is actually the true beta. You should learn to prove this. This is how we basically prove unbiasedness. What about the variance? Now you can prove the variance and use this to generate the variance for variance metrics. Now the variance of beta cap, we know it already. If you can remember, we said that it's expected value of the error squared. The expected value of the error squared. Now watch this. This very element here is the beta cap. This is also the expected value of the beta cap. Assuming unbiasedness, it means that this and this are 0. And if they are 0, it means that the expected value of 0 is 0. And so the beta variance becomes 0. Now, we also know that when you expand this, okay, watch this. If I expand this, I can now say that the expected value of beta cap minus beta, because remember, the expected value of beta cap here, beta cap here, beta cap here, okay. Oh, this is a typo. It should have been beta, not beta cap. Okay, it should be beta. So we can now say that this value here, watch this here. Okay, we've already defined this. The expected value of beta cap, and if you go back here, you see that beta cap is this, beta cap is this, beta cap is this, beta cap is this, okay? So the expected value of beta cap is this square. And on the basis of that, we can say that the variance of beta cap is this sigma multiplying by the sum of the xi, all divided by the sigma xi square, all square. And which can now be, you can pull out the sigma square, and then you can have everything here to the right, and pull this one backward. Okay? So it's like you have this one, but then you subtract, because when you bring the down one up, you have -2. But what is up there is -1 already. So you move it up to the numerator, and then eventually everything becomes -1. Now, it's very easy to show that the OLS has the smallest variance, meaning that it is blue. Okay? And if it has the smallest variance, then it is good for all unbiased estimators. As the beta cap is equal to this, we can say also that it's a linear combination of zero mean normally distributed with an independently identically distributed with a zero mean and a constant variance. We can say that because what you have, you've already proven unbiasedness for this. And so we can then conclude that the beta cap is normally distributed as a true beta and with the variance, which can be constant provided there is homoscedasticity in there. The classical assumption of what we've done is the simple case, or the bivariate case. In a multivariate case, the same thing happens. The expected value of the error is supposed to be 0. The variance and the covariance assumption that we knew of, we indicate that all the diagonals elements here, okay, are constant, and then the off-diagonal elements, are 0. And this will represent the principle of homoscedasticity. This is just a way of writing the homoscedasticity assumption in a matrix form for multivariate case, just for multivariate case. And it's the same thing that we have here, which we have explained. So let's recap the Markov theorem. The Markov theorem says that in this model, OLS is given by that. OLS is basically given by that. And you can find the OLS. Okay, you know where this is coming from. You know where everything here is coming from because you will derive it. If we substitute the y here, okay, we can substitute that y into this. We are finding for the multivariate case, the multivariate case of the variance of beta cap. That's for all of them. Because remember, everything is defined by both the mean and the standard deviation, or the mean and the variance. We just got to know the mean, the expected value, okay, which is this. So we can now know the estimate of this using the mean principle. We are just finding the variance. We can substitute this y with the x beta plus error. And then we can split them, because remember, everything here is multiplying this. So we can multiply everything here by this. That will kill off this 4. Okay, because one of them will have -1, the other will have +1. So that will be gone. So this part will be left to this, and then the rest will be multiplying the error. Then we can remember this assumption. If we take the expected value of this, the expected value of beta cap is going to be, for this is going to be beta. But for this, we need to take the expected value of the error here. And when you take the expected value of the error, that will finish it, because we know that is equal to 0. And therefore, the expected value of the beta cap here will be equal to the true beta. This is unbiasedness treated in a matrix form. The previous one, it wasn't in a matrix form. But this is in a matrix form because we are dealing with multivariate case. Okay. We are also aware of this. Okay. We know that the expected value of this is equal to that. Don't forget, we knew that from here. Okay. We knew that even from here. From here. Okay. So keep that in mind. And therefore, we can assume that x is fixed, or the independent variables are fixed. The multivariate case, how do you now find the variance, the covariance in a multivariate case? Well, the same principle will come from here. The same one we use for the bivariate case. Just take the expected value of the beta cap minus the expected value of beta cap, and then square all. That's what we used to do in a simple case. But here we take the prime. Okay? Because in here we have the error, and then in here we have the error prime. If we substitute this, we can say that the expected value of this minus, because the expected value of beta cap is actually beta. So we can just conclude, because we've proven unbiasedness already. So from unbiasedness, this boils down to this value, still with a prime. Okay. And so we can then substitute and find the variance of this. This is expected value, that's the mean. So we can find the variance by substituting whatever value this beta cap is. This beta cap, we know the value. Okay. This beta, we know the value. This beta cap, we know the value. The beta, we know the value. So we can now substitute these two. And when you do that, remember, we are still taking the expected values of these matrices. You can move the errors into the middle, kill off the x's, but the x's, some of them have got, to the power -1. Okay, for example, this one here, this very one there, and this one here. One is prime, one is x without a prime. And so when you bring this part together, you get x prime x. And that can cancel off this one, because this one too is x prime x, but it's to the power -1. And so this x prime x is actually to the power +1, which we don't write. So that can go, leaving us this. So we are now going to have expected value of that. In fact, this one is going to go. Okay. It's still there, but it's going to go. Expected value of epsilon prime epsilon. Epsilon prime. Okay. If I take the expected value of this epsilon prime, we already know the value. We can't touch this x prime x to the power -1. We can't touch it because it's not canceling. But this one, when it goes here, to cancel. Okay. This one cancels. If you take the expected value of epsilon prime, that will give you an identity matrix with the constant value. And so we can cancel off this. Now we are canceling it. And then conclude that the variance of beta cap is this. That is what the Excel will give you. That is what Python will give you. And that is what R will give you as well. So all of this goes to show that in a matrix form, we can actually derive. But that is what the software is doing that we don't see. If we assume that the error is independently and identically distributed with a zero mean, normally distributed with a zero mean and a constant variance, we can now conclude that the beta cap is normal, as each element is linear combination of the other variables. So given that we know the mean now, and we know the variance of beta cap, we can now say that beta cap is now distributed normally with this beta and with that variance. If the disturbances are IID, independently and identically distributed, but they are not normally distributed, we can also go ahead and show that beta cap is asymptotically normal. In other words, as you increase the sample size, beta cap will become close to beta. In other words, it will have this distribution if the sample size were infinite. That is like increasing it to infinity. It's the same thing. All right. We've already spoken about the variance, the variance of beta cap. We already know that. The residuals is also sometimes written like this. Take note. It's written like that, and we can replace this by this M value. Now, what is M? Well, if you check carefully from the previous one, M can be represented as identity matrix minus x prime, x to the power -1, x prime. It's actually the middle one that we cancel, but this time you have an identity matrix minus all of that. And so we can see that this error can be equal to my, okay? Which when you replace the y by this x beta plus r, we can say that it is equal to this, me, or me, because this mx is equal to 0. If you see x beta plus epsilon, this x beta plus epsilon, when you check this critically, it is not the same as E. Let me just put E, because this one is epsilon and this one is E, so that we don't confuse ourselves. Remember, this is a matrix, but it is mx beta plus that. And so mx, because mx is 0, whatever thing that is here will be left, it's there. So if this one is 0, we are just left with the m epsilon here. And that is what this one actually is. We can actually see that y minus the y cap, substituting the y cap can give you this matrix. Now, you will never use this my, but you will at some point in your work, especially when you're doing GLS, when you're doing GMM, they will be talking a lot about this, which you will use in your work. This one is a repetition of the same thing that I had here, okay? Because it's my equals to that. All of these goes to show you something very tiny, but very important when you want to prove that unbiasedness. When you want to prove unbiasedness of the residual term, of the variance, okay, for small sample size, especially this part here. For small sample size here, okay, you can see that the residual sum of squares divided by the sample size minus the explanatory numbers is the small sample variance. Okay. Provided you can prove that the expected value of the expected value of the estimate of the beta is equal to the true value, provided you can say that, then you can also prove that the expected value of the variance, the sample variance, is equal to the population variance. You can prove that. And what makes you be able to prove this is because of that conclusion that you have in the n minus k equals to that. Let's drop this one. This one, you don't need it. It will not make any difference. One of the things you will find is that once you found the estimate, once you have the beta cap, you can find several things. It can help you to find the goodness of it. It can help you to determine the R square. And to determine the R square, you need the TSS, ESS, and the RSS. Those ones are very easy. Okay, I will not go through them. But the key point is the R square itself. There are several ways you can write the R square and adjusted R square. One is the explain sum of squares over the TSS, which is the 1 minus the RSS over the TSS. In a matrix form, these are the matrix forms. The R square is always between 0 and 1. In a simple case, this is the formula for the adjusted R square. The difference between the R square and adjusted R square is that adjusted R square is penalizing the inclusion of irrelevant variables. So if the variables are irrelevant, the adjusted R square is going to be smaller than the R square. In the case when the two are the same, the R square and the adjusted R square will be the same, which means that there are no irrelevant variables in the model. But if they are, the R square will come down. It will never be more than the adjusted R square will come down. It will never be more than the R square, but it can be equal to the R square, provided there are no irrelevant variables in the model. Okay, so a benefit of all of these notation is that it gives you a simpler way of writing the OLS, in a normal equation, especially when they are matrices. Okay, just remember that the OLS normal equation can be written as this. Okay, and in a case of a matrix, full matrices, you can write them that beta cap is equal to their matrix. This way of writing the beta cap is an interesting one because it can be used by several ways to come with a conclusion. So that's it. Now, what I want you to do is I want you to look at this assignment. We wrote down the two normal equations for the regression. You remember this one, consumption is a function of income here. And then you have the error term. And then we indicated that when you substitute this one, you can set it to 0 and then expand this out and then come out with this and that and that. Now, what I want you to do is this. This we have gone through already, where we indicated as C is equal to the blah, blah, blah. I want you to derive the expression for the beta cap for this. Now, I did that, but I didn't use the consumption function. I want you to derive the expression for the beta cap. This time, using this one, not using the X and the Y that I did, but using the consumption and the income that you have here. So try that, the expression for the beta cap. How do you find the beta cap here? It's very easy, basically. The next one, we can write the regression model in question 1 in a matrix form. For example, when you come here, this whole thing, you can write it in a matrix form like that. What you're supposed to do is to show that these expressions for the beta cap, the alpha cap and the beta cap, prove that the value for this alpha cap here and the value for the beta cap are going to be beta cap being alpha cap over this. In other words, they are going to be this. Again, we did that in the previous case, but I did not use for the consumption case. So I wanted to use that for the consumption case. Okay. And then derive for the value of x prime x minus 1 x prime c, not y, but c. Derive that. The third one, suppose there are two explanatory variables, x1i and x2i. But then this first one is equal to a product of something and the second one for all I. Why are we unable to calculate the beta cap in this context here? Especially when you multiply the x2i by a rho value, why can't we find the beta cap here? What are we able to deduce from the effect of x1 and x2 on C? Again, using the original function that I gave you. Try and think through that because it's easy to see that we cannot calculate it anymore. Now, in a regression model, which includes a constant as an explanatory variable, okay, if you have a constant, okay, the total variation in the dependent variable, that is the TSS, is a sum over I of the squares of all the deviations around the mean. We normally calculate it like this. That's a TSS. Okay. Now, remember this time I'm not using the C, I'm using the Y as a dependent variable. Yours is to prove that this can be decomposed. This TSS can be decomposed into the explained sum of squares and the residual sum of squares, where the explain is this and the residual is that. I didn't prove that, but you should be able to easily prove that. Prove that this is equal to that. What makes this equal to that? Starting from here. Yes, to prove that. And then finally, check that you can obtain the expression given in the lectures for the OLS estimator in the multivariate case, where the model is written in matrix notation. Now, let me show you that. Remember, we are looking at the OLS estimator in the multivariate case. So let me just show you. So what is that? Okay, so this is the OLS estimator in the multivariate case. When you are using the C, check how you can find this in the multivariate case. Do that and let me know. Now, what you're going to do from here is that, so this is another assignment. What you're going to do from here is that next time we are going to use R to come to the practicalities of some of these. And then after this, we shall look at diagnostics. We shall dig more into diagnostics and then be able to do that. Any question, please? Is Albert around?